Hello, students! So, I was going to start this lecture by talking about a whole bunch of scientists and all the great things that they did for chemistry, but I decided maybe you guys are less excited about that and you're more excited about the actual chemistry that they discovered, but I still would be remiss if I did not talk to you about Bohr. Bohr, brilliant guy. Not going to get into him, but I will get into his model because it's still very useful today and it helps us understand how electrons go together and it helps us understand how elements behave. So let's get right into it and talk about his model. So we remember nucleus has protons and neutrons. That's the only thing that's giving us mass because the electrons are so small. And electrons are actually in Bohr's model. They're in these concentric rings, meaning rings inside of rings inside of rings around the nucleus. You can see the rings right here. If this is the nucleus, you'll see the rings right here. Remember that this is not to scale. They'd be much, much larger than this. Remember the nucleus is that little marble inside of the football stadium. But each ring holds a certain number of electrons, he figured out. That first level holds 2 electrons. It's small. It's very close to the nucleus. The second ring holds 8. Remember that 8. It's going to be important later. And the third holds 18. The fourth holds 32, so on and so forth. You really are only going to need to know first, second, third for most of what we're doing, at least right now. And this model is really important. Remember I talked about 8. That's because there's something called the Octet Rule. And that Octet Rule is that atoms are most stable if they have 8 valence electrons. All right, that's all well and good, but what the heck are you talking about, Mr. C? Octet, think of octopus. Oct means 8. Octagon, octopus. It means 8. So octet means it wants 8 valence electrons. One of these silly valence electrons. Well, I want you to think of a valet. A valet is on the outside of an establishment, and a valence valence means the outside shell, the outside ring, because that's what we're concerned about when we're talking about bonding and ions and electrons. It's that outside level, the valence level. So electrons could be on the inside, that first level, that first ring, or they can be further out. And ones that are on the outside have a lot more energy than the ones that are on the inside. And more energy means you want to do more things. That's what energy is. It's just the ability and the desire to do things. So if you are on that outside, you want to interact. You want to do something. And there's our valet. Remember, valet, valence. So let's talk about a couple of elements. Let's talk about neon first. So neon has 10 protons. Where do we get that from? Yes, we can use our periodic table and we can use the atomic number to get that 10 protons. Let's figure out the number of neutrons. Remember, you're going to use the atomic mass, 20, rounded of course, minus the atomic number, 10, to get 10 neutrons. And if we're talking about neutral neon, you're going to have 10 positive charges from the protons, which means you need 10 negative charges. Where do we get negative charges from? Yes, you get them from the electrons. So we need to add 10 in there. And we're going to add them inside out. We're going to start in the middle, or start where there's lower energy and then go to the higher energy. So there's 1, there's 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, you'll notice there's 2 in the inside shell, which means that there's 8 in that outside shell. And what's that name for that outside shell? that outside ring, yes, that's the valence ring, which means those are valence electrons. And if it has 8 valence electrons, what's our rule? Yes, it's happy. It's the octet rule. We want that 8 valence electrons. So let's talk about oxygen. Oh, oxygen, it's got 8 protons. That seems like a good sign. Let's figure out its number of neutrons. Neutrons are 16 minus 8. That's 8 neutrons. And now let's figure out the electrons. Remember, we're going to go inside out. And how many electrons do we need if we have 8 protons? Yep, it's 8. So let's add them in. 1, 2, 3, 4, 5, 6, 7, 8. All right. However, that, maybe my math's off. That seems like it's only 6 electrons in that outside ring, that valence ring. Let's see. 1, 2, 3, 4, 5, 6 valence electrons. That is an unhappy atom. It wants to be stable. It wants 8 electrons. It wants 8 electrons. What can be done to satisfy this horrible tragedy? Well, we'll get there. We'll get there. Let's talk about a couple more examples. Let's talk about magnesium. So magnesium, it has 12 protons. Remember from our atomic number. We calculate out the, and we'll think electrons. We know 12 protons. We've got 12 electrons. We can see them right up here. Let's think about those neutrons. Yes, it's 24 minus 12. With these small elements, it seems like it's always going to be the protons and neutrons and electrons are always going to be the same. That's not always the case. You have to do this math for the higher level elements. Make sure you remember that. But in this case, it is 12 neutrons. And now let's add in our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. Uh-oh. I think we have another issue again. We've got these 2 electrons on that outside there. They're in this new valence shell, these 2 valence electrons. And that's, again, a sad magnesium. And then oxygen we've already gone through. We've got 8 electrons, 8 neutrons, 8 protons. We see them going in. We know the tragedy that's about to unfurl. We've got another sad atom. But don't worry. Something can happen because we'll notice magnesium's got 2 in this valence shell. Oxygen, it's got 6. It needs 2. Oh, wait. Something can be done. We can move this electron over. And we can move this electron over. Ooh, look at him move. Look at him move. And now, what has happened? It seems that both of these elements are now happy. Let's figure it out. But okay, we had 12 electrons. We don't have 12 anymore. We now have 10 electrons. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, and on this valence shell, there's 8. Oh, let's check oxygen. We've got 8 electrons, but we added 2 more. There's now 10. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8 in that valence shell. What? I think something has changed here. I think we no longer just have atoms. I think we have ions. Yeah, we have ions. And they're ions because there's now a different number of protons and electrons. We're going to talk about this a little bit later, but there's 2 more protons now than there's electrons. So now we have 2 more positive charge. We have a positive ion. That's called a cation. We'll talk more about that later. In oxygen, it has 8 protons, and now it's got 10 electrons. Now it has 2 more negative charges than positive charges. So now we have an anion. And in fact, anions, they go by their own special name. They end in a new suffix. It's called oxide. It's called oxide, and you'll see that very soon. But let's think about our valence now. Instead of having the 2 on the outside and the 6 on the outside, now we have, well, there's our oxide ion up there, our oxide ion. And now let's think about our valence. We've got 8 valence. You can count them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And that means we have 2 happy atoms. They had to move some electrons around. They had to become ionized. They had to become ions. You can see these ions here now. But that is really how ions are formed. It's just a transfer of electrons. It can't be protons. It can't be neutrons. It's just going to be electrons that move around in order to get that happy octet in that valence shell. However, with every rule, there is going to be exceptions. The exceptions are helium and hydrogen, and this is just because they have very low atomic numbers. So helium, remember, has an atomic number of 2. If we calculate it out, we have our neutrons as 4 minus 2. We've got 2 neutrons, and if we've got 2 protons, that means how many electrons do we have to have? 1, 2. And how many fill that first shell? Well, yeah, it's 2. It's full. It's happy. Hydrogen, we see 2 valence. We see happy. Hydrogen, it only has 1 proton. It's got an atomic number of 1. Oh, that's interesting. So if you calculate out the neutrons, it's 1 minus 1. Well, yeah. In most cases, hydrogen has 0 neutrons. Now we know about deuterium. We know about tritium from what we've done earlier, or Pogil. But we know those are isotopes. Remember, isotopes. But the most common isotope of hydrogen has 0 neutrons. So now let's talk about their electrons. We've got 1 proton. That means 1 electron, 1 valence. Well, it's not happy. It's not happy like helium, but it really only wants 1 more electron so that it does have that full valence shell, and then it is happy. So these are the exceptions to the octet rule. Think octet, think happy, but always when we're talking about very low elements, helium, hydrogen, they're happy with just a couple of those little electrons. So let's talk about ions. Ions are really just atoms that have a charge. They can be positive or they can be negative. I always remember cations. I really like cats. So this is my happy little cat Telly. I always get positive feelings, and I actually think of cations in a positive way. So that's it. And these lose electrons. These lose electrons. That gives you a positive charge. Anions, these have a negative charge, and that's going to be a 2 minus, or this is a 1 minus. You don't have to write the ones. It's just an understood 1 minus, or just 1 plus. You can just write as plus. And these gain electrons. They have more negative charge. So let's think about our magnesium from 2 slides ago. It had 12 protons. It had 10 electrons. So that means it has a 2 plus charge. So magnesium ions are always written as Mg2 plus. Oxygen, on the other hand, it has 8 protons. After it had gained the 2 electrons, you add 2 more minuses, so it now has 10 negatives, and this should actually be a 2 here. You have a 2 minus, so you have oxygen 2 minus, and that's actually called an oxide anion, an oxide ion. And you see this very angry looking woman. That reminds me of an ex that I have. named Anna. This is not actually a picture of her, but sometimes she was angry. And so you can think of Anna, my ex, or angry ions, or negative ions. Negative ions.